Welcome to Thought Frontier.
Welcome back, everyone, to another deep dive. Today, we're not just talking about seeing atoms, right? We're going way deeper. We're going to be looking at how scientists are visualizing the details inside single atoms. It's incredible.
It really is.
Yeah.
Like for so long, we've had these blurry pictures of atoms, and now it's like we're getting high-definition images that actually show us how they work on the inside.
Yeah. It's a total game changer, and we've got three really fascinating sources to dig into today. So first up, we've got this 2017 scientific article. It's all about a revolutionary technique for visualizing the electric fields within individual atoms, and they do it using a specialized electron microscope. Pretty cool, huh?
Definitely.
And finally, we'll dive into a 2023 news piece. It's about this really powerful new imaging method that lets scientists observe electrons interacting around atoms with incredible precision.
Yeah, it's amazing how these discoveries build on each other. It really shows how rapidly our ability to see and manipulate the atomic world is evolving.
It's like we're climbing a mountain, right? We started with this hazy view from the foothills, and now we're at the summit. It's a crystal clear perspective of the atoms that literally make up everything.
You know, that's a pretty fitting analogy given some of the visualizations we'll be discussing.
Okay, so let's start with that 2017 article. Let's talk about this incredible technique they used. What was it called? Differential phase contrast stem.
Yeah, or DPC stem for short. It's a big step forward from traditional electron microscopes.
Oh, yeah, for sure. Because even with those advancements, like annular dark field stem, which sounds super fancy, we were mostly just seeing the positions of atomic nuclei, right? Like a shadowy outline of the atom.
Exactly. We knew they were there, but we couldn't really see much of their internal structure. DPC stem, though, that changes everything.
Okay, so how does that actually work? I mean, how do you go from blurry blobs to actually seeing inside an atom? That's crazy.
It's all about how electrons interact with electric fields. So traditional electron microscopes, they just measure the intensity of the scattered electrons.
Got it.
But DPC stem, it measures how the electrons are deflected by the electric field, not only of the nucleus, but also the surrounding electrons.
Okay, so instead of just getting an overall intensity, DPC stem allows us to map those subtle deflections. And that reveals the detailed electric field within the atom.
Precisely. And, you know, the distribution of charge within an atom, that's what dictates its electric field.
Right, right.
So what DPC stem is essentially doing is allowing us to see how the charge is distributed within a single atom.
Wow. That's incredible. We're not just seeing an atom, we're seeing its internal structure.
Exactly.
It's like upgrading from a grainy black and white image to a full color HD picture.
Yeah, and the researchers, they tested this out on both the crystal and on isolated gold atoms. And in both cases, the electric field maps that they obtained, they matched up perfectly with the theoretical predictions.
Wow. So that confirmed that they were really seeing the internal structure.
Yeah.
Not just some artifact of the imaging process.
Exactly. It opened up so many possibilities. Like, think about it. Now we could potentially see how the charge distribution within a molecule changes during a chemical reaction.
Whoa, that's like watching the reaction unfold in real time.
Yeah.
At the atomic level?
Yeah.
That's insane. But the 2017 article, they did mention some limitations, right?
Right. DPC stem, it works best on isolated atoms or very simple structures. When you have more complex crystals, the diffraction patterns, they get really messy, and that can obscure the signal.
So it's like trying to listen to a single conversation in a really crowded room.
Exactly. So as groundbreaking as this technique is, it's not, you know, a magic bullet. There's always room for improvement.
But it's still a huge leap forward.
Oh, absolutely.
Okay, so we've gone from shadowy images to seeing inside atoms. And now let's talk about that 2007 article, the one about trapping and imaging 250 individual atoms. That just sounds like a massive milestone, especially for quantum computing.
It was huge. I mean, quantum computers, they rely on qubits, right? And those are often individual atoms that are held in very specific quantum states.
Right. And one of the big challenges with building practical quantum computers is keeping those atoms stable, right?
Yeah, exactly.
And in those specific states.
Exactly. And this research, what they showed was not only could they trap and image this large number of atoms, but they could keep them stable for long periods of time. Yeah. And that's crucial for any kind of reliable quantum computations.
So 250 atoms might not sound like a lot, you know, just in general.
Right.
But for quantum computing, this was enormous, wasn't it?
Oh, absolutely. Being able to scale up the number of qubits you have while keeping them stable. That's a major hurdle. This research, though, it offered a really promising path forward.
So they did all of this using cesium atoms and lasers. Can you explain how that works? Because that sounds really complicated.
Yeah, so they use this technique called laser cooling. And what that does is it slows down the cesium atoms. And then they use something called an optical lattice. Imagine like a 3D grid, right, made out of light. Each point on that grid can hold a single atom.
So it's like a tiny little cage, invisible cage made of light that traps the atoms in place.
Precisely. And the level of control they had was incredible.
Yeah.
The trapped atoms, they had incredibly low, what we call hopping rate.
Hopping rates. Okay.
Less than 5 times 10 to the negative 6 per second.
Okay, so basically they were locked in and ready for those quantum calculations.
Right. And what's fascinating is that they were also able to achieve zero entropy with these trapped atoms.
Okay, now you're using the science terms. Can you break down what zero entropy means in simple terms? I'm not a physicist.
Sure. Think of entropy as a measure of randomness or disorder. So zero entropy means there's absolutely no randomness in the system. All those atoms, they're in this perfectly ordered state with no uncertainty about their position or their energy levels.
So it's like having a perfectly organized library, right?
Yeah.
Every book is in its exact spot. No chaos, just pure order.
A perfect analogy. And this order, it's absolutely crucial for quantum computing because any randomness, any uncertainty, it can disrupt those super fragile quantum states and cause errors in calculations.
Oh, that makes sense. And this ties into decoherence, right? That thing we always hear about with quantum computing.
Exactly. Decoherence is any kind of external interference that messes with those quantum states. Like trying to write on a chalkboard while someone's shaking it.
You get a blurry mess.
Yeah. Your message becomes unreadable.
Okay, that's a great analogy. So these trapped atoms, they were much less vulnerable to decoherence because they had that zero entropy and long-term stability,
Right.
which could really pave the way for more reliable quantum computers.
Absolutely. This research was a major win in the quest to build them.
Okay, so from blurry shadows to seeing inside atoms, now we're trapping hundreds of them with mind-blowing precision. It's starting to sound like science fiction.
Yeah. And it gets even more exciting. Now, we'll delve into that 2023 news piece and see how scientists are using these advanced techniques to not just see atoms, but to actually manipulate the electrons around them.
All right, I'm hooked. This sounds incredible.
It really is. This research focuses on this unique material called samarium hexaboride. And get this, it acts as both an insulator and a conductor.
Wait, so it's like a light switch that's both on and off at the same time?
Yeah, kind of.
That's crazy.
It's wild. Scientists have been trying to figure out how that's possible for decades. And this new imaging technique, it gives us a way to actually see what's happening at the atomic level.
So I'm guessing this involves more than just a regular microscope, right?
You bet. They took a scanning tunneling microscope and modified it to detect magnetic resonance. Now, this doesn't directly show us the electrons, but it reveals their location indirectly by sensing their magnetic interactions.
So they're like using magnetism to feel the electrons, even though they can't actually see them?
Exactly. And the resolution they achieved is mind-blowing. It's single atom precision.
Wow.
We're not just seeing atoms, we're seeing the individual electrons interacting around them.
That's incredible. What did they see using this method?
Well, they were able to create these topographic maps of electron density. Imagine like a mountain range.
Okay.
The peaks and valleys represent areas of high and low electron density.
Oh, that's cool. So they could pinpoint exactly where those electrons were on the surface of the material.
Exactly. And that's where the potential for building quantum devices comes in.
Ooh, hold on. This is so fascinating, but I think we need to take a quick break. We'll be right back to uncover how those electron maps could help create quantum devices. Don't go anywhere.
We were talking about those topographic maps, right? The ones with peaks and valleys representing the density of electrons.
Right, and how those could actually help build quantum devices. You were about to explain that when we took our break.
Yeah, exactly. So remember that research from 2007? They used lasers to make a sort of optical lattice to trap atoms.
Yeah, I remember that.
Well, imagine doing something similar, but with electrons instead.
So instead of trapping atoms with light, we're talking about trapping electrons. But how do you even trap something that tiny and slippery?
That's where those density maps come in. See, by manipulating the atoms on a material like samarium hexaboride, researchers can create little electron corrals, basically.
Yeah.
They can kind of nudge those peaks and valleys, those areas where the electrons are more or less dense, to make specific spots where the electrons are more likely to hang out.
So it's like they're building these tiny little electron playgrounds.
Yeah.
And using atoms to sort of guide the electrons where they want them to go.
Exactly. It's a great way to put it. And those playgrounds, that's where the qubits could be. By controlling where those electrons are and how they behave,
right,
we can encode and manipulate quantum information.
So these electron corrals, they're not just about seeing the electrons, but about controlling them, shaping their behavior to actually build the components of a quantum computer.
Exactly. And this technique, it could help with a major challenge in quantum computing, protecting those fragile qubits from interference from the environment. Remember we talked about decoherence.
Yeah, the shaking chalkboard analogy.
Right. Well, these corrals, they could act like little shields to protect those trapped electrons from getting disrupted by the outside world.
So just by carefully moving the atoms around on a surface, you can not only make qubits, but also create safe spaces for them, make them more stable, less prone to errors.
Yeah, exactly. It's a huge step toward making quantum computers more practical.
It really is. We've come a long way from blurry images of the nucleus. Now we're talking about manipulating individual atoms and electrons, building quantum devices piece by piece at the atomic level.
Yeah, it's amazing what we can do. And it's not just about quantum computing either. Think about the possibilities for materials science.
Oh, right. If you can control atoms and electrons with this level of precision, you could, I don't know, maybe create materials that have never existed before.
Exactly. Stronger, lighter, better conductors, maybe even materials that can change their properties on demand.
Wow.
Yeah, the possibilities are endless. This ability to manipulate the building blocks of matter could revolutionize so many fields. Medicine, energy, manufacturing, almost every aspect of our lives, really.
I can see how this might be a lot to take in for some of our listeners. We're talking about controlling the fundamental pieces of the universe.
It is pretty mind-blowing, but it's also incredibly inspiring, I think. We humans, we have our limitations. But we've developed these tools, this intelligence, to explore and manipulate the universe at its tiniest level.
It is humbling, but it's also really empowering. It shows what we can do when we keep asking questions and pushing the boundaries of what we know.
Absolutely. And this is just the beginning.
Yeah.
Who knows what we'll discover next as we continue to explore the atomic world?
It really is an exciting time. This deep dive has really opened my eyes to how much progress is being made in these fields. It feels like we're on the edge of a technological revolution, driven by these advances in atomic imaging and manipulation.
Yeah, it's a really exciting time to be alive, especially if you're fascinated by the universe like we are.
Definitely. These discoveries really show that even the smallest things can have a huge impact.
That's true.
Now, before we wrap up today, I want to leave our listeners with a thought-provoking question. We've seen how scientists are moving beyond just looking at atoms to actually manipulating them. So my question is, now that we can control these tiny building blocks of matter, what are we going to build with them? What amazing inventions are waiting to be discovered in this new era of atomic precision? What do you think?
Wow, that's a big question. And I think it's one that's going to shape scientific exploration for a long time. We've talked about quantum computers and new materials, but it really feels like the possibilities are endless, doesn't it?
It's almost overwhelming to think about. Imagine creating materials atom by atom, making things that are stronger than anything we know, or maybe even substances with properties we can't even imagine right now. Or what about medical treatments that can target individual cells with atomic precision?
Yeah, it's mind-blowing. And those are just a couple of examples. But we have to remember that this kind of power comes with responsibility, right?
Yeah.
As we get deeper into the atomic world and we can control it more and more, we have to be careful. We need to make sure we're using these discoveries ethically.
For the good of everyone, absolutely. We need to be having those tough conversations about the potential consequences of these technologies, both the good and the bad, and make sure that everyone benefits from these discoveries, not just a few people.
Exactly. We need to use these powerful tools to build a better future for all of humanity.
Well said. This deep dive has been an incredible journey. From blurry images of atoms to the amazing possibilities of manipulating matter at its most basic level. I hope our listeners have enjoyed exploring this with us.
It's been a pleasure. It always amazes me to see how far human ingenuity can take us, and I can't wait to see what's next.
And on that note, we'll wrap up this episode of The Deep Dive. Thanks for joining us, everyone, and keep those brains exploring.